Welcome to my channel, AI Depth School. Hi all, this is my very first video. With this video, I'm starting my YouTube journey. Today, we're diving into one of Gen AI's biggest unsolved problems. Every major AI model, ChatGPT, Claude, Gemini, they all hallucinate. They make up facts with complete confidence. And here's the shocking part. This isn't getting better, even in the latest models. Today, I'm breaking down groundbreaking research from OpenAI and Georgia Tech that finally explains why this happens, and more importantly, how we can actually fix it. Let's go. Let me show you how bad this really is. I asked 3 of the most advanced AI models a simple question. What was the title of Adam Kalai's PhD dissertation? Look at these answers. ChatGPT says it was about boosting and online algorithms, completed in 2002 at CMU. DeepSeek claims it was algebraic methods in interactive machine learning at Harvard in 2005. And Llama, efficient algorithms for learning games at MIT in 2007. 3 completely different answers, different titles, different years, different universities. And here's the kicker. None of them are even close to correct. Every single detail is fabricated. This isn't a rare bug. This is happening constantly. So why does this happen? It all comes down to what I call the birthday problem. Think about how AI models learn facts. When Einstein's birthday appears 100+ times in the training data, the model learns it perfectly. When someone moderately famous appears 5 to 10 times, the model gets it right sometimes. But here's where it breaks down. When a fact appears just once in the training data, like in someone's obituary, the model is basically guessing.
And the math here is brutal. There's actually a formula. If 20% of facts in your training data appear only once, you're guaranteed at least a 20% hallucination rate. It's not a bug you can patch. It's a mathematical consequence of how these models work. The model literally cannot distinguish between what it learned once and what it's making up. Now here's where the research gets really clever. The team proves something fascinating. Generating correct text is fundamentally harder than just classifying whether text is correct. Think about it like this. If I show you a sentence and ask, "Is this valid?" That's a yes or no question. That's classification. But if I ask you to generate a valid sentence from scratch, that's way harder. And here's the mathematical proof they discovered. Your generation error rate is at least twice your classification error rate. So if you can't reliably tell what's valid from what's fake, and remember, some facts only appear once, you definitely can't generate valid responses. This connects hallucination to decades of research on classification errors. And those errors are well understood. They come from statistical complexity, poor models, and noisy data. Hallucinations aren't mysterious anymore. They're just classification errors in disguise. The researchers identified 3 main statistical causes of hallucinations during training. First, arbitrary facts. Things like birthdays, phone numbers. There's no pattern to learn. If it appears once, the model is rolling dice. Second, poor models. Sometimes the model architecture itself can't handle the task. We'll see an example of this in a moment. And third, GIGO. Garbage in, garbage out. If your training data contains conspiracy theories and misconceptions, guess what? Your model learns them. What's crucial here is that even with perfect training data, no errors whatsoever, you still get hallucinations from causes 1 and 2. This isn't just about cleaning your data. It's baked into the mathematics of how these models learn. Let me show you how spectacularly spectacular these models can fail at simple tasks. I asked, how many D's are in the word DeepSeek? The correct answer is 1, just 1 D at the beginning. But look at what these models said. 2, 3, 6, even 7. They can't count letters in a simple word. This is a poor model problem. These models don't see individual letters. They see tokens or chunks. DeepSeek gets broken into D, Eep, Seek, so the model can't actually count the letters because it never sees them individually. Reasoning models like O1 solve this by thinking step by step, literally spelling out D, E, E, P, S, E, E, K. But standard models, they're fundamentally limited by their architecture.
Now, here's where things get really interesting. If hallucinations start during training, why doesn't post-training fix them? You know, all that reinforcement learning and fine-tuning that happens after? Here's the answer, and it's going to blow your mind. Imagine you're a student taking a test, and you don't know an answer. Option A, write, I don't know, guaranteed 0 points. Option B, guess confidently, 50% chance you get points. What do? You guess, obviously. That's rational test-taking behavior. Now, here's the problem. AI models are always in test-taking mode. They're evaluated on benchmarks that score them like exams. And just like students, they learn that guessing when uncertain beats admitting uncertainty. We're not just failing to fix hallucinations, we're actively rewarding them.
Don't believe me? The researchers analyzed the 10 most influential AI benchmarks, the ones that determine which models get deployed, which companies win. And look at this. 9 out of 10 give 0 credit for saying, I don't know. GPQA, MMLU Pro, SWE Bench, Math, all binary grading. Either you're right or you're wrong. There's no credit for appropriate uncertainty. Only Wildbench gives minimal credit for uncertainty. And even then, it's unclear if IDK scores better than a fair answer with some hallucinations. This isn't just an academic problem. When Google and OpenAI report their model scores, these are the benchmarks they use. These scores determine everything, and every single one rewards confident guessing over honest uncertainty. Let me make this crystal clear with a thought experiment. Imagine 2 models. Model A is honest. When it's uncertain, it says, I don't know. Model B is dishonest. It always guesses confidently, even when it has no clue. Under current benchmarks, Model B will score higher, always, because it gets partial credit from lucky guesses while Model A gets 0. So which model gets deployed? Which one gets the press release? Model B, the dishonest one. This is why hallucinations persist despite billions in research funding. It's not that we don't know how to reduce them, it's that we're measuring success in a way that encourages them. We've created a system where lying is rewarded and honesty is punished.
Okay, so how do we fix this? The researchers propose a 2-part solution. Part 1 is mathematical. Improve the training objectives. Include uncertainty in the loss function. Balance accuracy against coverage. Use better error penalties. This is important, and the algorithms exist. We just need to implement them more widely. But part 2 is the game changer, and it's socio-technical. We need to change how we test these models, not create new benchmarks. We need to fix the existing ones that everyone already uses. Because here's the thing, you can train the most calibrated, honest model in the world, but if MMLU and GPQA still reward guessing, that model will never get deployed. It'll score too low. The industry follows the benchmarks. Fix the benchmarks, fix the incentives, fix the models. That's the path forward. So, what does fixing the benchmarks actually mean? The solution is beautifully simple. Explicit confidence targets. Let me show you the difference. Old prompt. What is the capital of France? That's it. The model has to answer, and if it guesses wrong, it loses everything. New prompt. What is the capital of France? Answer only if you're more than 75% confident. Correct answer, plus 1 point. Wrong answer, minus 3 points. I don't know, 0 points. Look what this does mathematically. If you're 80% confident, your expected value from answering is plus 0.2. If you're only 60% confident, answering gets you minus 0.6, but saying I don't know gets you 0. Honesty is now optimal.
The confidence threshold can be whatever we want, 50%, 75%, 90%. The key is making it explicit in the instructions. Now there's a clear, objective rule. No debates, no ambiguity. And most importantly, the model is rewarded for appropriate uncertainty. Why is this approach so powerful? 3 reasons. First, it's objective. There are clear rules that everyone agrees on. No arguing about whether the model should have known something. Second, it's testable. We can verify that models are properly calibrated across different confidence thresholds. If a model says it's 80% confident, we can check if it's right 80% of the time. And third, this is huge. It's scalable. We don't need to create entirely new benchmarks. We just add one paragraph to the instructions of existing benchmarks. MMLU, GPQA, SWE bench, all of them can be updated. And because these are the benchmarks the industry already uses, adoption is realistic. This makes honesty mathematically optimal without requiring everyone to rebuild their evaluation infrastructure. All right, let's make this practical. What can you do about AI hallucinations right now? First, ask for confidence levels. Instead of just asking a question, say, "How confident are you?" Only answer if you're more than 80% sure. This works surprisingly well even with current models. Second, request sources. Always ask the AI to cite where it got information, especially for anything critical. This forces it to ground its answers. Third, cross-check everything important. Medical advice, legal information, financial decisions. Never trust AI alone. Use it as a starting point, not the final word. For developers, use calibrated models and build uncertainty into your apps. Let your users know when the AI isn't sure. And for the field, support uncertainty-aware benchmarks. When you see papers or products, ask about their hallucination metrics, not just their accuracy. Vote with your attention and your compute resources. Let's zoom out for a moment. This research teaches us something profound about AI. Hallucinations aren't some mysterious bug that proves AI is fundamentally broken. They're predictable mathematical consequences of how we train and evaluate these systems.
The real problem isn't the models, it's the incentive structures we've built around them. We've created a system that rewards confident guessing over honest uncertainty. That's not a limitation of artificial intelligence. That's a design choice made by humans. And here's the hopeful part. Design choices can be changed. We built these evaluation systems. We can fix them. This isn't about waiting for some breakthrough in AI capabilities. It's about aligning our metrics with what we actually want. Trustworthy systems that know when they don't know. Let's wrap this up with the 3 key things to remember. 1. Hallucinations have mathematical roots in the training process. Even with perfect data, if facts appear rarely, models will hallucinate. That's just statistics. 2. Current benchmarks reward guessing over honesty. 9 out of 10 major evaluations give 0 credit for uncertainty, so dishonest models score higher and get deployed. 3. We can fix this by changing how we evaluate AI. Explicit confidence targets make honesty mathematically optimal. And because we're modifying existing benchmarks, not creating new ones, adoption is realistic. The next time an AI tells you something with complete confidence, ask yourself, is it actually certain, or is it just optimized to sound certain? That distinction matters. If you found this valuable, smash that like button and subscribe for more deep dives into AI research. Drop a comment with your experience with AI hallucinations. And remember, we can build trustworthy AI, but only if we measure trustworthiness. See you in the next one.